Generative AI refers to a category of artificial intelligence models designed to create new content, whether text, code, images, audio, or even 3D structures, based on learned patterns from massive datasets. Unlike traditional algorithms that follow pre programmed rules or predictive models that estimate future values, generative AI produces original responses based on prompt inputs. These models don't just recognize patterns, they reproduce them in novel forms. Popular examples include OpenAI's ChatGPT, Google Gemini, Anthropic's Claude, and image generators like Midjourney. The key behind their power lies in their architecture. Most are built on transformer based large language models that understand context and relationships across tokens, enabling high level reasoning, creativity, and language generation. Unlike conventional rule based or statistical AI, generative AI is not limited to recognizing and labeling input. It can produce new, coherent outputs. For example, a traditional AI model might classify whether a voltage reading indicates overload. In contrast, generative AI can write a report explaining the cause of the overload, suggest fixes, or even write firmware code to handle it. This creative capacity arises from pre training on large corpora, followed by fine tuning, enabling the AI to generalize across scenarios and domains. Its relevance expands beyond creative industries into engineering, healthcare, legal analysis, and scientific research, making it a valuable augmentation tool for technical professionals like electrical engineers. Generative AI is revolutionizing the way electrical engineers solve problems. Instead of relying entirely on manual design iterations and software specific skills, engineers can now use natural language to describe tasks, and AI tools generate relevant circuit schematics, simulation scripts, or embedded code. This shift lowers the entry barrier for complex tasks, fosters creativity, and significantly accelerates design timelines. Whether you're building a microcontroller based system, performing load calculations for a transformer, or debugging a faulty protection relay, generative AI can assist in real time. By acting as a knowledgeable co pilot, it improves accuracy, productivity, and innovation across disciplines. In real world electrical engineering, the applications of generative AI span a wide range. Power system engineers can prompt AI for load flow analysis, substation relay coordination, or fault simulation. Circuit designers can use it to convert written descriptions into SPICE ready netlists or generate schematics automatically. For control system engineers, AI can create tuned PID algorithms or describe state machine logic for automation processes. In embedded systems, engineers can receive STM32 or Arduino C code based on sensor logic and communication requirements. Even renewable energy engineers can simulate solar inverter behavior or battery management routines using prompt driven workflows. These use cases demonstrate that generative AI is not just a novelty, it's a productivity booster across all specializations. Beyond operational efficiency, the impact of generative AI in electrical engineering lies in its ability to streamline collaboration and expand innovation. Engineers can co develop with AI to quickly test concepts, create reports, or summarize datasets. Technical documentation that once took hours can now be drafted in minutes. This speeds up engineering reviews, regulatory filings, and design handovers. For junior engineers, AI acts as a mentor, producing code, visualizations, or explanations on demand. For teams, it acts as a common knowledge base, supporting cross disciplinary collaboration. Whether you're working on renewable energy optimization or firmware for a sensor node, generative AI helps electrical engineers work smarter, faster, and together. In generative AI, the structure of a prompt determines the accuracy, completeness, and relevance of the output. Electrical engineers use prompts for two major purposes: instructional, to generate designs, diagrams, or code, and analytical, to interpret sensor data, simulations, or test logs. Knowing how to construct each prompt type helps engineers get outputs that match real world engineering needs. Let's start with instructional prompts, used to direct the AI to build, write, or design something specific. These are helpful for generating schematics, code, or documentation from scratch. The AI interpreted the design requirements, input output voltage, current, and generated a text based simulation ready circuit file. No analysis was required, just conversion of design logic into code. Now let's look at analytical prompts. These are used to ask the AI to evaluate, diagnose, or explain something already done, such as simulation results, test logs, or control logic performance. Here, the AI analyzed the described electrical condition, reasoned through performance bottlenecks, and recommended fixes. No generation occurred. This was purely diagnostic. To clearly distinguish the two prompt styles, let's compare them side by side. This table helps students quickly categorize prompt goals, allowing them to use the right structure in labs, design reviews, or debugging sessions. Whether you're generating something or analyzing it, structure matters. Clear prompts get clearer responses. Here's a checklist to refine your prompt structure. These elements help generative AI model your expectations more precisely, improving technical relevance and usability of the results. In this session, we clarified how the purpose of a prompt, whether to instruct or analyze, drives its structure. Instructional prompts help engineers generate tangible outputs like netlists or block diagrams. Analytical prompts help explain simulation behavior or sensor anomalies. Mastering this distinction allows electrical engineers to guide generative AI more effectively across a wide range of design and testing workflows. Generative AI models respond differently based on how many examples you give them. Whether you provide 0, 1, or a few examples in your prompt changes how well the model understands your intent, especially in precise domains like electrical engineering. In this lecture, we'll explore the three core techniques: zero shot, one shot, and few shot prompting, each with electrical use cases. Zero shot prompting works when the task is common, straightforward, or when the AI has seen similar patterns before. Without any examples, the AI guessed what elements go into a solar PV system based on the wording. This is efficient for standard tasks but may lack precision for niche specifications. In one shot prompting, you provide one example to teach the model your preferred structure or tone. With one structured example, the AI aligned tone, format, and precision to match the original, useful for documentation and test logs. Few shot prompting shines when your task is nuanced and you want the AI to generalize from a handful of examples. The AI learned how to convert specs into design logic and applied the pattern from previous examples to a new scenario. Each technique has its place depending on task complexity, domain familiarity, and desired consistency. Engineers can use this table to align their prompt strategy to their need, speed, precision, or pattern learning. This lecture showed how different prompting techniques affect the AI's ability to reason and respond in electrical engineering workflows. Zero shot is fast, but may be vague. One shot teaches formatting. Few shot helps build reusable logic patterns for design. By tailoring input styles, engineers can convert AI into a precision tool for simulation summaries, transformer specs, and code generation, making their workflows both faster and smarter. Complex engineering tasks often cannot be completed with a single prompt. They require multiple steps, each building on the previous. This is where prompt chaining becomes essential. In electrical engineering, prompt chaining enables you to go from high level design specs to detailed code, simulation ready files, and even narrative reports by sequencing several focused prompts. Let's begin with the user defined electrical specification. The first prompt translates this into component level design logic. The AI interprets specifications and selects viable components using power electronics domain knowledge. This forms the base for chaining. Next, we pass the selected component ratings to a second prompt to generate a SPICE simulation. The AI maps the values into a syntax ready netlist compatible with NGSP-ICE or LTSP-ICE. This is now a runnable simulation. After running the simulation, you may want AI to explain the waveform or debug inefficiencies. The AI performs reasoning based on typical circuit behavior, identifying causes and adjustments using simulation interpretation knowledge. Finally, prompt chaining lets us produce a summary report or documentation that engineers can present. AI formats engineering outcomes into a concise professional document, replacing the manual summarization process. This session demonstrated how engineers can string together multiple prompts to move from concept to simulation to reporting, mirroring real world engineering pipelines. Prompt chaining is more than automation, it's a design methodology that brings AI into each phase of the engineering cycle. It enables rapid prototyping, reduces iteration time, and produces end to end deliverables without constant rephrasing. For electrical engineers, this turns complex projects into executable sequences driven by intelligent prompting. When working on repetitive engineering tasks, like designing transformers, explaining power flow, or generating PCB documentation, it's inefficient to start every prompt from scratch. That's where reusable prompt templates come in. By designing structured prompts with placeholders, engineers can repeatedly use them for different projects by simply changing input variables. Transformer winding design can be automated by templating the steps needed to optimize efficiency, core material, and cooling. The prompt abstracts the problem while retaining specificity, replace values, and reuse across projects with consistent logic and formatting. Explaining power flow in networks, especially during training or fault analysis, benefits from natural language narratives. This reusable structure helps simulate classroom explanations or report sections where clarity is key. Narratives adapt to your system specs. Documenting PCB designs is time consuming, especially when repeating for multiple boards. A prompt template can convert design data into clear reports. Once created, this template enables fast and repeatable documentation of PCBs without manually compiling notes. This lecture demonstrated how reusable prompt templates can accelerate engineering documentation and design across multiple contexts. Whether you're designing transformers, interpreting system flow, or writing PCB summaries, templates remove the need to rephrase every time. This not only boosts productivity, but also ensures that your outputs remain logically structured, domain accurate, and presentation ready, empowering engineers to work smarter with AI at their side. Electrical engineers spend significant time converting design intent into circuit schematics and simulation ready code like SPICE netlists. With generative AI, this process can be accelerated. AI can interpret plain text specifications and produce detailed circuit descriptions. complete with component ratings and simulation ready files. Let's begin by converting a textual spec into a verbal circuit design. This step ensures the AI understands the electrical topology. This natural language response forms a verbal schematic. It's useful for documentation, teaching, or narrative generation before moving to code. Now let's convert the same specs into a SPICE netlist, usable in LT SPICE, NGS SPICE, or PSPICE. The AI structured the text into a complete netlist, setting up nodes, simulation time, load, and waveform for the switching signal. This output can be copied directly into SPICE tools for testing. For presentation or documentation, you may want a block level summary of your circuit's operation and function. This prompt enables readable documentation with correct sequencing and engineering terminology, ideal for design proposals and academic write ups. Some AI platforms can even convert text based prompts into visual diagrams. If integrated with drawing tools, you can generate basic schematics or logic flowcharts. While not always dimensionally precise, the diagram gives a fast visual representation that can be improved in KiCad or Eagle, excellent for whiteboards, PDFs, or team discussions. This lecture revealed how generative AI can translate your engineering intent into ready to use circuit documentation and simulation code. Whether you're starting from verbal specs or need simulation ready SPICE, structured prompting can replace hours of manual translation and formatting. AI becomes your design assistant, producing not just the logic, but the narrative and code to test it. PCB layout is a critical phase in electrical engineering, influencing circuit reliability, EMI EMC compliance, thermal performance, and manufacturability. Traditionally done with EDA tools and engineering expertise, it can now be enhanced with generative AI. By crafting the right prompts, engineers can receive actionable design recommendations on component placement, trace routing, grounding, and thermal considerations. Let's begin with how to prompt AI to suggest optimal component layout for a given board. AI evaluated thermal dissipation, EMI zones, and signal integrity principles. The suggestions act as pre layout guidelines before using tools like Altium or KiCad. Routing impacts both signal fidelity and EMI/EMC compliance. AI can assist in formulating routing strategy across layers. The AI explained practical rules like 3W, spacing, return path continuity, and isolation of noise prone signals, all key for robust PCB design. Compliance with EMI/EMC is non negotiable for most products. AI can draft a pre layout checklist aligned with common regulatory frameworks. The AI distilled layout strategies for passing emissions and immunity tests, CISPR 22, EN55032. This checklist can accompany early board reviews. Thermal performance determines the long term reliability of components. AI can offer layout level heat management suggestions. The AI recommended passive cooling measures at layout level and helped estimate copper surface needed for thermal dissipation, saving thermal simulation effort. This lecture illustrated how generative AI can function as a virtual layout advisor, helping electrical engineers apply best practices in PCB design without deep diving into each datasheet or standard manually. With well structured prompts, you can generate intelligent placement strategies, pre layout compliance reports, and routing rules. This accelerates your prototyping phase and ensures that you're not starting from a blank board every time. Transformer and motor design is a cornerstone of electrical engineering, demanding precision in magnetic materials, winding arrangements, core geometry, losses, and thermal performance. Traditionally, this involves iterative calculations and finite element simulations. With generative AI, engineers can now use well-structured prompts to generate core design specifications, optimize materials, and simulate outcomes, accelerating R&D while maintaining accuracy. Let's begin by asking AI to determine transformer winding turns for given voltage and frequency. The AI applied transformer design equations using target flux density P max equals 1.2 Tesla and cross sectional area A equals 12 square centimeters. Selected wire sizes based on current and estimated losses using empirical values. Material selection affects both efficiency and cost. Let's ask AI to recommend materials based on transformer rating. AI listed materials based on industry grade loss tables and use case suitability. This enables engineers to choose based on efficiency or economic constraints. For motor design, we need to minimize copper and iron losses while maintaining torque. AI can optimize this through configuration suggestions. The AI used standard templates and design curves to recommend an efficient layout, including materials and thermal mitigation methods. Finally, we can ask AI to visualize winding configuration and prepare content for documentation or simulation. The AI included electrical fuzz or logic, core limb descriptions, and layout insights suitable for documentation, manuals, and E-Day design files. This session highlighted how generative AI can guide engineers through critical design decisions for transformers and motors. By combining domain specific prompts with AI's vast contextual knowledge, users can generate design ready specs, optimize loss performance, and produce layout ready documentation. This doesn't replace simulation, but significantly accelerates the early design and validation phase, offering a productivity leap in traditional electromechanical design. In control engineering, logic implementation must be both precise and understandable, especially when deploying PID loops, fuzzy controllers, or finite state machines, FSMs. Generative AI helps transform control theory into narrative logic, ideal for documentation, stakeholder explanation, or code scaffolding. By prompting AI, engineers can quickly create interpretable, step by step representations of how control logic operates, even before simulations or PLC implementation begin. Let's begin with tuning a PID controller. AI can produce a parameter recommendation along with a plain language explanation of how the controller behaves. The AI calculated a moderately aggressive PID profile and translated control dynamics into an understandable narrative, perfect for stakeholder reports or documentation. Fuzzy logic controllers are ideal for systems where behavior isn't strictly linear. AI can help us generate membership functions and rule tables for such applications. The AI created a concise rule base with logical inference, fuzzified ranges, and smooth actuation transitions. It's deployable in MATLAB Fuzzy Toolbox or embedded fuzzy engines. State machines define how a system transitions from one mode to another, ideal for multi stage automation or error handling flows. AI can narrate state diagrams and even generate pseudocode. The AI created a clean transition logic aligned with control system practices. It narrates behavior flow, ensuring clarity for both implementers and reviewers. In this session, we saw how AI transforms complex control logic into accessible narratives. Whether it's PID tuning rationale, fuzzy controller setup, or process driven state transitions, prompt based AI interactions help engineers clarify, communicate, and document logic with ease. These outputs support simulation, PLC deployment, and training by removing ambiguity and enhancing transparency in system behavior. Embedded systems form the heart of modern automation, from IoT devices to industrial controllers. Traditionally, writing embedded code for platforms like Arduino or STM32 requires experience in low level C or assembly programming. With generative AI, developers can rapidly prototype, test, and optimize embedded logic using well structured prompts. This dramatically reduces time to deployment and helps non programmers contribute to firmware design. Let's begin by asking the AI to control fan speed using PWM on an Arduino based on temperature input. The AI correctly mapped sensor values to PWM output. It also included temperature conversion logic and safeguards against overdriving. Code is well structured for debugging and can be uploaded as is. Now let's move to STM32 programming using HAL libraries to blink an LED with a 1 second delay. The AI used STM32 cube syntax accurately, recognizing GPI toggling and HAL delay integration. It scaffolded the necessary function calls for startup and clock setup. Embedded communication is key for debugging or device interfacing. Let's generate UART code for an STM32 to send temperature values every second. The AI computed voltage from ADC, converted it to temperature, and formatted the message using SPRINTF. It then transmitted using blocking UART functions, ideal for basic debugging or interfacing. This lecture demonstrated how generative AI transforms embedded development into a prompt driven workflow. Whether using Arduino for quick prototyping or STM32 for industrial applications, engineers can now scaffold I/O handling, signal processing, and communication protocols within seconds. Beyond speed, the AI generates clean, well commented, and standard compliant code, helping junior engineers, students, or cross functional teams accelerate firmware delivery without sacrificing quality. Power flow analysis, also known as load flow analysis, is a fundamental task in electrical power systems. It determines the voltage, current, active and reactive power flows across a grid under steady state conditions. Traditionally solved using methods like Newton-Raphson or Gauss-Seidel, this task can now be simplified and narrated by generative AI. With well-crafted prompts, LLMs can help engineers write power flow equations, explain results, and debug mismatches without going deep into code or matrices manually. Let's ask the AI to help explain the three key types of buses in a power flow system. The AI classified bus types clearly with electrical use cases, making it ideal for technical documentation or classroom slides. Next, we'll prompt the AI to generate a simple Newton-Raphson based power flow code in MATLAB for a 3-bus system. The AI auto-generated a Newton-Raphson template, including initialization, mismatch formulation, and convergence logic, saving 2 to 3 hours of manual setup. Let's say the Newton-Raphson method fails to converge. We'll use the AI to interpret common causes. The AI generated domain specific insights and practical engineering suggestions like shifting the slack bus or revalidating PQ inputs, ideal for troubleshooting documentation. Finally, let's summarize a hypothetical power flow result into a business readable narrative. The AI translated numeric outputs into a performance summary useful for executive presentations or compliance documentation. This lecture explored how generative AI simplifies power flow analysis. From generating code to interpreting load flow results, AI acts as both a tutor and assistant, speeding up scripting, validating electrical assumptions, and helping engineers communicate findings more effectively. Whether you're a student building your first 3 bus model or a professional optimizing substation reports, AI makes this once manual process faster, smarter, and easier to explain. Load forecasting is vital for ensuring grid stability and economic power generation. It involves predicting future electricity demand based on historical usage and external factors like temperature, seasonality, and events. Traditionally, this required time series models, data preprocessing, and manual reporting. But with generative AI, we can now synthesize natural language narratives from raw data or model outputs. The result? Rapid, explainable forecasts ready for both engineers and executives. Let's use a prompt to summarize seasonal demand changes using past consumption data and temperature records. The AI extracted seasonal cycles and correlated them with temperature patterns and calendar events, replacing hours of manual Excel or script analysis. Now we'll generate a natural language daily forecast that includes contextual drivers. The AI converted inputs, temperature, day type, trend, into a professional narrative, perfect for daily dispatch reports or grid operator briefings. Let's create a 3-day load forecast with weather driven variability included. The AI generated a structured outlook with cause effect detail tied to weather variability, supporting grid planning and reserve allocation. Finally, we'll generate an executive summary that blends recent demand, weather impact, and near term outlook in a single report. This polished summary integrates historical and predictive narratives into a cohesive format for leadership reporting without any spreadsheet formatting. This lecture illustrated how generative AI can convert raw load forecasting data into clear, contextual narratives for engineers, planners, and executives. From seasonal trends to daily heat wave impacts, AI generated forecasts are fast, interpretable, and scalable. They enable better decision making by making demand variability transparent and eliminate hours of data crunching and formatting. Fault analysis and protection system design are foundational to electrical engineering. They ensure the safety and stability of power systems during abnormal conditions like short circuits or equipment failures. Generative AI can now assist in generating fault classification narratives, relay setting calculations, and protection coordination strategies. By using targeted prompts, engineers can simplify documentation, interpret complex current time behavior, and generate relay logic for use in SCADA or PLC systems. We'll begin by prompting the AI to classify fault types and explain typical causes and locations. The AI offered structured descriptions aligned with standard textbooks, ready for fault study sections or protection guides. Now let's request relay settings for an 11 kilovolt feeder with a known fault level and CT ratio. The AI calculated relay settings step by step and justified curve type, streamlining protection grading and breaker coordination. Let's now interpret a TCC curve to understand relay response at various fault levels. The AI mimicked an engineer's analysis by extracting curve behavior, quantifying time current margins, and guiding practical coordination steps. Finally, let's summarize the full protection plan for a substation, including fault study, relay logic, and zone coordination. The AI produced a comprehensive protection design report ready for submission or review, blending numeric logic with professional narrative. In this lecture, generative AI was used to streamline fault detection narratives, relay setting recommendations, and coordination summaries. These tasks, which typically span hours across Excel, relay manufacturer catalogs, and protection software, were condensed into prompt driven outputs. Engineers can now focus more on reviewing protection strategies rather than formatting or drafting protection logic. MATLAB and Simulink are central to modeling, simulation, and validation in electrical engineering. However, building simulation ready models manually, especially for complex systems like converters, control loops, or power electronics, can be time intensive. Generative AI offers a new pathway where you can describe your system in plain English, and the AI returns MATLAB scripts or Simulink model block descriptions automatically. This speeds up prototyping, reduces syntax errors, and helps you quickly iterate. We'll begin by generating a MATLAB script for simulating a basic DC motor using its differential equations. The AI converted system equations into a functioning MATLAB simulation, ideal for academic assignments or rapid prototyping in labs. Next, let's ask the AI to generate a Simulink block diagram description for a buck converter system. The AI described how to place and configure blocks in Simulink, acting like a tutorial walkthrough. It allows users to recreate the model visually. Let's now model a feedback control loop using a PI controller in MATLAB for a temperature control application. The AI created a control system simulation from scratch, automatically structuring the control loop, ideal for PID tuning experiments. Finally, we'll auto generate test bench code for validating the buck converter performance. The AI built a complete validation pipeline that could be run post simulation, excellent for automating testing in model based design. This lecture demonstrated how generative AI can eliminate MATLAB slash Simulink entry barriers by turning text into simulation ready code. Engineers can now go from system descriptions to functioning models in minutes, perfect for prototyping, education, and production development. The AI ensures structure, correctness, and clarity, transforming the way control systems and power electronics are simulated. Finite element method, FEM, is essential for solving complex electromagnetic problems in electrical engineering, from simulating electric field distribution in insulators to modeling inductance in magnetic cores. These simulations are traditionally performed in platforms like ANSYS Maxwell or COMSOL Multiphysics, but interpreting results and documenting simulation assumptions are time consuming tasks. With generative AI, we can prompt for narrative summaries, mesh refinement suggestions, and even COMSOL script templates to accelerate design cycles. Let's begin by describing a cylindrical conductor and requesting the boundary conditions and mesh setup using AI. The AI offered a precise and simulation ready description useful for Maxwell or COMSOL setup. It's a time saver during model initialization. Will generate an interpretation of the resulting field plot, focusing on stress points and areas of concern. The AI interpreted post processed FEM output and suggested mitigation strategies, imitating the role of a seasoned electromagnetic engineer. Now let's ask for a scripting template to automate COMSOL's ACDC module simulation for a magnetic core. The AI structured a valid COMSOL script template usable in model automation workflows, ideal for batch processing or parametric sweeps. Finally, we'll use AI to generate a professional simulation summary, something typically required in engineering design documents. The narrative is publication quality and ready for project reports, client presentations, or compliance documentation. This lecture showed how generative AI empowers electrical engineers in FM workflows, from model initialization to report generation. It translates geometric and physical descriptions into meshing rules and boundary assignments. More importantly, it contextualizes numerical results into engineering insights. Engineers can now streamline electromagnetic simulations in Maxwell or COMSOL, removing the bottleneck of writing technical summaries or managing parameter sweeps. In electrical engineering simulations, edge cases and fault scenarios play a critical role in validating robustness. Whether you're stress testing a motor drive, triggering overvoltage in converters, or injecting faults into power system simulations, scenario generation is both complex and vital. Generative AI can automate this process by reading test data, identifying failure points, and generating plausible what if scenarios, test matrices, or simulation directives. This creates a fast lane for experimentation in tools like Simulink, MATLAB, or COMSOL. Let's begin by using historical test data to build a fault scenario matrix for an inverter system. The AI created a structured matrix highlighting test scenarios with engineering logic tied to hardware safety thresholds. This replaces manual design of test conditions. Now let's generate a narrative simulation description for an edge case involving simultaneous low voltage and high load. This scenario setup helps validate the resilience of drive systems to supply instability, supporting model based testing in Simulink or PSIM. Next, we'll write a test bench script that programmatically injects a short circuit fault into a converter system. The AI builds fault aware simulation code that can be modified for any converter topology, great for test, validation, and safety threshold checks. Finally, we'll prompt the AI to generate a simulation result summary suitable for documentation or report inclusion. This type of AI generated post simulation narrative accelerates lab reporting, design reviews, and presentation building by summarizing key metrics with context. This module demonstrated how generative AI enhances simulation workflows by generating fault scenarios, creating test matrices, and summarizing outputs. Engineers can now scale their robustness testing with less effort and more confidence. Whether you're injecting short circuits, voltage drops, or signal loss, AI can design, trigger, and narrate complex test cases. This ensures that models not only perform but endure edge conditions and real world anomalies. Technical writing and literature review are foundational to any engineering thesis, product development, or R&D effort. Yet engineers often spend weeks combing through dense research papers, patents, and white papers. Generative AI can dramatically reduce this effort by summarizing large volumes of content, generating formatted citations, comparing research findings, and even reviewing patent claims. With the right prompts, AI becomes a co author in technical documentation, helping you build content faster and with more academic integrity. Let's begin by asking the AI to summarize multiple PDFs or abstracts into a concise review of methods and outcomes. The AI parsed abstracts and conclusions, merged similar outcomes, and synthesized a domain relevant narrative. Next, we'll ask the AI to format citations for the summarized papers using IEE style. The AI applied formatting rules to titles, author names, journals, volume issue numbers, and publication years. Let's analyze a patent abstract and ask the AI to compare it with known research or products to assess novelty. The AI scanned for overlap with existing publications and highlighted both novelty and known techniques, useful in patent drafting and evaluation. Finally, let's prompt the AI to generate a background or methodology section for inclusion in a technical report. The AI produced well structured academic prose suitable for inclusion in reports, grant proposals, or thesis submissions. In this session, we saw how generative AI can assist not just in simulations or design, but also in scholarly writing and intellectual property tasks. Literature, reviews, citations, and patent comparisons often take up weeks. But with prompt based automation, electrical engineers can focus more on research depth and less on formatting or summaries. AI becomes a reliable co pilot in academic and technical documentation workflows. Documenting experiments and engineering activities is a crucial but time consuming part of any electrical engineering workflow. Whether you're running lab tests on circuits, logging voltage, current data, or validating simulation outcomes, raw data needs to be turned into structured reports. With generative AI, you can auto generate experiment logs, summarize test results, and create professional engineering reports directly from CSV files, table snapshots, or manual logs. This saves time while maintaining precision, traceability, and readability. Let's now auto generate sections of an engineering report, including introduction, procedure, and conclusion. The AI generated coherent, technically correct narrative sections aligned with academic and industrial standards. Finally, let's generate a submission ready markdown report with headings, tables, and summary paragraphs. The markdown format enables immediate upload to project repositories, LMS portals, or integration with Git based documentation. With this module, we demonstrated how engineers can automate the process of documenting their lab experiments and test. From test logs to formal reports, generative AI transforms raw data into formatted, insightful records. This reduces human error, ensures report uniformity, and allows students and professionals to focus on analysis rather than repetitive formatting or transcription. AI becomes a silent assistant in every lab session, capturing, narrating, and compiling. Creating technical presentations and engineering diagrams can often be tedious, especially under tight project deadlines. Engineers are expected to turn designs, research, and test results into concise visual communication tools like slides, block diagrams, and flowcharts. With generative AI, this process becomes significantly faster. Whether it's summarizing technical content into slides or generating circuit, system, or signal flow diagrams, AI tools like ChatGPT, DALL-E, Gemini, and Copilot can bridge the gap between raw knowledge and polished presentation. Let's begin by generating a full slide outline for a technical presentation on DC-DC converter efficiency. The AI structured the entire presentation flow, offering both slide titles and key discussion bullets to guide the presenter. Now let's generate diagrams, block level or schematic, directly using text prompts and AI image tools. Using visual generation models like DALLE or Mermaid integrated into Copilot, the prompt led to a clean architecture diagram suitable for slides or documentation. Let's create script ready markdown content that can be imported into slide generators or documentation platforms. AI generated structured markdown content compatible with tools like MARP, Obsidian, or Git based slides, ideal for technical pitches and classroom instruction. Finally, let's prompt the AI to generate a visual flowchart that maps a typical engineering workflow, such as embedded system development. The AI outlined the control flow, decision nodes, and transitions, offering export ready content for online visualization or printed reports. This session shows how generative AI can act as a visual design partner for electrical engineers. From slide decks to schematic illustrations, it can produce structured, accurate, and domain specific visuals on demand. Engineers no longer have to struggle with PowerPoint formatting or Visio blocks. AI fills that gap, freeing teams to focus on content and innovation. Whether it's a classroom project or a conference pitch, AI driven visuals boost clarity and impact.